Good morning to all of you.
Good morning.
Morning, sir.
Good morning. So, is my screen visible?
Yes, sir.
Yes, sir.
Okay. So, are there any questions, doubts?
Sir, I had one question actually.
Yeah.
So while formulation of this weak form, you had mentioned that generally the order of the differential equations should be even.
Yeah.
But suppose if that is an odd order differential equation, then we will integrate till there is some meaning of the like terms we are having,
Yeah. Yeah.
right?
See, because every time you integrate, you get boundary terms. So, those
Yes,
boundary terms should be meaningful.
yes, sir.
So, you will do the integration by parts till you get the meaningful boundary conditions. Basically, the boundary terms, whatever we get.
Yes, sir. So my question was like, so generally, like in what kind of problem this situation will arise? Because like the questions which we have done till now, in
Yeah.
that mostly we had the order differential equations, right?
Yeah.
So can we have one of the examples for the odd one also?
Yeah, I will. I think the maybe I'll have to find out and then I can give you in the next class. Yeah, I will give you that example next class.
Okay, sir. Thank you, sir.
Yeah. So if there are no more questions, let me start.
Hello, sir.
Yeah,
Sir, like previous class, you have given one problem to formulate weak form and use variational integral.
yeah,
Uh, if one in one equation, there is two equation. In one equation, it is for axial force and another equation for transverse force. So,
yeah.
if for axial force, if two boundary conditions are there for transverse force, also one boundary condition is there in the term weak form, and for axial force is there, then we have to put both the boundary conditions, means primary
Yeah,
variable and secondary.
you have to combine that. So that is what I had told, no, that if there are two or more boundary terms involving the same weight function, so then you'll have to combine those terms. I'm going to discuss that anyway. I will discuss that.
Okay, okay, sir. Okay, sir.
Yeah. So let me start then. So I'm continuing with the big form. So last problem I had given you to try, so I'm going to discuss the same. So if you remember those equations, so let me directly write the weighted residual statement. So the problem, as I had told you, is that there is a rod and it can have any boundary condition, although here I am fixing at the left end. So x direction displacement is u and y direction the displacement is v, and there is a distributed force af along the x direction, and similarly there is a distributed force uh, q along the y direction, and the length of the rod is l. So for this I had given you two differential equations. Now if you look at the weighted residual statement of equation 1, weighted residual statement of equation 1. So that is now there, since there are two differential equation involving two different variables u and v. So we will have to have, in general, we would require different weight functions for both the differential equations. So the first equation we take the weight function as w1, and for the second equation the weight function as w2. So the better, let me take a minus sign out. So we will have integration 0 to L for the first equation. The weight function I am taking as W1, and then we will have the equation is EA into du by dx plus half of dv by dx whole square minus f dx is equal to 0. So this is what is going to be the weighted residual statement for equation 1. And in this case, if you, I think, yeah, I missed this d by dx over here. So we have d by dx of this time. So in this case, if you look at, again, we want to distribute the derivatives. So the big form would be, big form for this equation would be the we do the integration by parts for the first term. So we will have minus w1 and then ea into du by dx plus half of dv by dx whole square. This is evaluated at 0 and L. Then minus minus plus integration 0 to L dw1 by dx. And then we will have this EA into du by dx plus half of dv by dx whole square dx. And then we will have minus integration 0 to L w1 f dx is equal to 0. So this is the big form of no, the first equation, which is straightforward. So we have, because the highest order derivative of, if you look at the u here is second, so we distribute the derivative this from here to here in the integral term. So whatever we get is the big form, and now the derivatives of u and w1 are same, so we stop here the integration by parts. So now if you look at the better residual statement of second equation, better residual statement of equation 2. So now equation 2 is, you now I had given you the differential equation, so only thing is that we take the weight function as w2, so the integration 0 to L w2, and then now the equation is d2 by dx square of ei into d2v by dx square minus d by dx of this ea into dv by dx into du by dx plus half of, so this is the same differential equation what I had given, this, and minus q dx is equal to 0. So this becomes the no, you check the brackets of course, and so this becomes the better residual statement, and then the weak form comes from the integration by parts. So now in this case, if you look at the first term, now this term, highest order derivative of v is fourth derivative. So we need to do the integration by parts twice to distribute the derivatives between w2 and v equally. So the first term would require the integration by parts only, or integration by parts twice. Whereas the second term, if you look at it, is minus w2 into d by dx of this EI. So the highest order derivative will be second derivative. So we have to do the integration by parts only once for the second term to distribute the derivative between uv and w2. So now the, for the first term, if we do the integration by parts twice, so we will get first boundary term would be w2 d by dx of ei into d2v by dx square, the limits 0 to L, and then minus dw2 by dx into ei into d2v by dx square, the limits 0 to L. And so these two terms come when we do the integration by parts twice for the first term. and then plus we will have integration 0 to L d2 w2 by dx square into ei into d2v by dx square dx. So this is as far as the first term is concerned. Then the second term, as I said, we need to do the integration by parts once. So the boundary term would be minus w2 ea dv by dx and then du by dx plus half of dv by dx whole square. So this whole term, now the whole term is evaluated at 0 and L, and then minus minus plus integration 0 to L dw2 by dx, yeah, and the derivative of the first function and the integration of the second. So because this derivative is there, that will go. So the integration of the second term would simply be d2 ea into dv by dx into du by dx plus half of dv by dx whole square dx, then minus of course integration 0 to L w2 q dx is equal to 0. So this is the weak form of the second equation. So now if you look at the, when we want to identify the boundary terms, hello, am I audible?
Yes, sir, audible.
Okay. So now if you look at now the first term, we want to identify the primary and secondary variables. So now if you first term, if you look at the boundary term is this particular term, and this equation comes from the equilibrium of forces along x direction. So in place of w1 we take u, so that would be primary variable and this will be the corresponding secondary variable. And now when coming to the second equation, so you see there are three boundary terms. If you look at this boundary term and this boundary term, both of them are involving w2, so you have to combine them actually. So no, w2 you take common and whatever you get inside that will be there. So now in place of, because this second equation comes from the equilibrium of forces along y direction, so we take w2 equal to v. So v will be one of the primary variable and the other boundary term is dw2 by dx. So the dv by dx will be the another primary variable. So these are going to be the primary variable and there would be corresponding secondary variables. So if you look at the primary variables and corresponding secondary variables, so the first primary variable, as we said from the first equation, in place of w1 we take u, so whatever we get that is the primary variable, and the corresponding secondary variable, the multiple the term which is multiplied with w1 in the first equation, first boundary term, so we will have the secondary variable as ea into du by dx plus half of dv by dx whole square. So this will be the corresponding secondary variable. Then we look at the second equation. So there is a w2 in the boundary term. So in place of w2 we take v. So that would be the primary variable, and the corresponding the secondary variable is going to be combination of, now we are taking this w2 common in these two boundary terms, so whatever we get that will be the secondary variable. So the secondary variable is going to be d by dx of ei into d2v by dx square, and minus from here minus ea into dv by dx into du by dx plus half of dv by dx whole square. So that for, see, now you will have to now when you have this, whenever you have this kind of a situation where no there are more than one boundary term involving the same form of the weight function, so you need to combine them. So like in this case we have combined these two no boundary terms. This boundary term and this boundary term we have combined. So the primary variable v and corresponding secondary variable is this, which is the combination of these two terms. And the third primary variable is another boundary term which is left out is this boundary term. So this involves dw2 by dx. So in place of w2 we write v. So dv by dx is the primary variable. dv by dx is a primary variable, and the corresponding secondary variable is ei into d2v by dx square. So yeah, these are the primary and secondary variables for this problem.
So,
Yeah.
so the third primary variables I think should be d2 d2v upon dx squared, no sir, because in the second boundary term the weight function is of the second order.
No, this
Here,
is
sir.
no, the first. This is the first derivative only, no, dw2 by dx. So we write
Post.
w2 is equal to v. So it becomes dv by dx as you see from this.
Okay, okay,
And
okay,
sir,
sir.
why we
Yeah,
aren't
I
considering
got it.
minus sign
Thank you,
there?
sir.
Yeah, yeah. So somebody else was why we are considering? Yes, please tell me.
Sir, why we are not considering minus sign in secondary variable for dv2 dv
Yeah,
by
see
dx?
you can actually take with the sign or you can take without sign. So both would be, when you write, both would be valid as far as they are, because what we are just looking at the form, but when we relate it to the physical quantities like the axial force, shear force, and bending moment, then we will have to appropriately take the sign. You can also take minus ci into d2v by dx square as the secondary variable, corresponding secondary variable. But why I have not taken is because if you look at basically this is axial force, this is negative times of the shear force, and this is the bending moment. You can take it as minus, then it would be negative times of the bending moment. So you can write both ways, both would be correct. Okay.
Okay, sir.
Yeah. So next is next is now we want to derive the corresponding integral functional. So to get into the integral functional, because we have now two weight functions. So one is W1. So in W1 is we have taken with the equation corresponding to equilibrium of forces along x direction. So W1 we take as variation in the corresponding displacement. So delta U, and W2 is taken with the sum of forces along y direction. So W2 we take as delta of V. So W1 is variation in U and W2 is variation in V, the displacement along y direction. And let us also, whatever the forces are there at the two boundaries at left and right, so axial force, shear force, and bending moment at left, axial force, shear force, and bending moment at right. So also let us take those. So this let us say that this EA into du by dx plus half of dv by dx whole square. This whole thing at 0 is, let us say, q naught, and the same thing at x is equal to L is, let us say, QL. And then we also have the shear forces. So shear force is, let us say, d by dx of EI d2v by dx square. That's a secondary variable corresponding to v, minus CA into dv by dx into du by dx plus half of dv by dx whole square, and this at the whole term. No, so the whole term at x equal to 0 is, let us say, minus v naught, negative times of the shear force at left end, and the same thing at x is equal to L is, let us say, minus VL. And then we have this EI into d2v by dx square. This is at x equal to 0 is, let us say, m naught, bending moment at left end, and EI into d2v by dx square at x is equal to L is, let us say, ml. So based on these, and now see, we may have any number of governing equations, then the corresponding weighted residual statements and the weak forms. But when we try to write get the integral functional, so that's a single functional. So we have to combine, now add all the weak forms together. So that is what you have to do. So now we combine, based on these, taking w1 as delta u and w2 as delta v, and all these the representation of the variables, we finally combine the big
Sir,
forms.
hello.
Yeah, yeah.
How can we physically interpret that the second that V naught, the whole expression corresponding to shear force?
Yeah, so this is for a large deformation problem. See, for the small deformation where dv by dx is small, you have only this term.
Yes, sir.
But for the large deformation, see what happens is, because the slope is finite, dv by dx is finite. So when you look at the, let us say, at a particular location x, the shape of the beam is like this. So this axial force, the axial force which will be there is going to be this EA into the axial strain, which is EA, the axial force is EA into du by dx plus half of dv by dx whole square. So this is going to be the axial force, and this force can be resolved into two components, one along the neutral axis of the beam, so in this direction, another a component in this direction. So these components basically with a negative sign adds with the shear force d by dx of ei into dv by dx square, which is there here. So that is how it comes.
Okay.
Yeah. See, this axial force is EA into du by dx plus half of dv by dx whole square, and then you take the component along the normal to the beam. This component gets added with this d by dx of EI into d2v by dx square. So that's how that is how the second term is coming. So now combining the weak forms, the two weak forms we have got for the purpose of writing down the expression for the integral function. So first weak form is now based on the whatever approximations, the notations we have used. So minus delta UL into QL plus delta U naught. UL is the axial displacement at x is equal to L, and U naught is the axial displacement at x equal to 0. So delta U naught into Q naught plus this is the the same integral term of the first equation. So now since the variation and differentiation are interchangeable, so we can write delta of basically dw1 by dx, and which is du by dx. So this is delta of du by dx, and then we have EA into du by dx plus half of dv by dx whole square dx. Uh, Here you will have dx, and minus integration 0 to L delta U F dx. So this is the first big form, plus we are going to add the second big form. So from the second big forms we'll again have the four boundary terms. So minus delta VL into capital VL plus delta V naught into capital V naught minus delta dv by dx at L into ml plus delta of dv by dx at x equal to 0 into m naught. So these four terms are the boundary terms from the second weak form. So we are adding simply that, and then the integral terms from the second weak form. So we will have integral 0 to L delta of d2v by dx square, and then ei into d2v by dx square dx, and then we have this plus integration 0 to L delta of dv by dx, and then we have ea into dv by dx into du by dx plus half of dv by dx whole square dx. So, and the last term from the second big form is integration 0 to L delta v q dx, and because both the big forms are separately 0, so their summation will also be 0, so the whole thing is actually equal to 0. So now we get the whole thing as no equal to 0. And now no, we want to take no, as I explained you that to write the big form, now the integral functional, we take the delta common out. So now from this we are going to take the delta common. So now we want to write this delta into common thing. So if you look at the first the bound, let me first write the boundary terms. So we have u naught q naught minus ul into ql, plus we have v naught into v naught minus vl into vl, mine plus uh, plus dv by dx at x equal to 0. So dv by dx naught into m naught minus dv by dx at L into ml. So these are all the boundary terms. So we take just delta common out from there. And then now if you look at, see this you have to do carefully. No, you should try to understand that carefully. So if you look at this term, this particular term, so this is straightforward. You have delta of d2v by dx square into ei into d2v by dx square. So when we take delta common, we will have half of ei into d2v by dx square whole square. So that is a straightforward thing. But now if you look at the second term, so the second term, now if you look at this one, so here you have now this CA into du by dx plus half of dv by dx whole square. So that term is there. And now if you look at this particular term, this term, in this also this one of the term is this EA into du by dx plus half of dv by dx whole square. So this term is actually common. So in both these terms, that is this term and this term, if you take this du by ea into du by dx plus half of dv by dx whole square as common, so then other term what you get is actually delta of du by dx plus no dv by dx into delta of dv by dx. So that you will see is nothing but delta of du by dx plus half of dv by dx whole square. And so then you have you can take the delta common. So this you should look at carefully. So first I am writing that term. So finally we can say the no, this term and this two terms, that is this term and no, this term, no, this one I am talking about, no, this whole term. So this term can be written as half of integration 0 to L, and then we can write that as EA into du by dx plus half of dv by dx whole square dx. Whole square is there. So EA du by dx plus half of dv by dx whole square, and then whole square, the square of the whole term, as you see here. So these two terms, now when you take delta common, this term and this term, These two terms can be written simply as this, and you can verify that when you take delta of this, so you will get half and 2 will get cancelled, so you will get EI into du by dx plus half of dv by dx whole square into delta of that, and when you take the delta inside, you will get delta of du by dx plus dv by dx into delta of dv by dx. So it will be same what we have got these terms here. And then of course this term is straightforward, so that is plus half of integration 0 to L EI into d2v by dx square whole square dx. And then of course minus integration 0 to L, we have u into f dx minus integration 0 to L, we have v into q dx, and this whole thing is equal to 0. So now is that clear? Are there any doubts in this? Hello, am I audible?
Yes, sir, you are audible.
Yes, sir. You are.
Okay, so have you got this? How I am writing the the inside term is in the delta, combining the two terms together. The EA terms, two EA terms are combined together.
Yes, sir.
Yes, sir. It's a
Okay,
simplification, sir.
yeah. So now you can say that this can be written as delta of I equal to 0, and where the integral functional or total potential energy functional integral functional I will be equal to this whole term. So that is u naught q naught minus ql plus v naught minus vl plus dv by dx naught in m naught minus dv by dx at l into ml plus half of integration 0 to L EA into du by dx plus half of dv by dx whole square dx plus integration 0 to L EI by 2 d2v by dx square whole square dx and minus integration 0 to L u f dx minus integration 0 to L vq dx. So this is your integral functional. And now if you want to look at the physical interpretation of the various terms, so if you look at the beam, now the forces are now, let me write these forces. So this is your q sorry f, so this is f and this is q. The boundary forces would be here q naught, v naught, capital V naught, m naught, this side capital QL, VL and ML. So these are forces. So you can directly identify the potential of all these forces. And if you look at the corresponding displacements at the two ends, so displacements are no u naught here, and in this direction v naught and dv by dx at x naught. Then you have here ul, you have VL, and you have dV by dx at L. So these are the displacement. Of course, at any point at the center you have U, and this is your V. So you can directly interpret the potential of these externally applied forces. So if you look at the first term U naught into Q naught, so see this is the force and this is the displacement. So they are in the opposite direction. So the work done is negative, potential is positive. So you get potential as U naught Q naught. Then similarly here this is QL and UL, both are in the same direction. So the work done is positive, potential is negative. So similarly now if you look at this force capital V naught, this displacement is small v naught, capital V naught and small v naught are in the opposite direction. So the work done is negative, potential is positive. This end, if you look at this VL and this VL, they are in the same direction, so the work done is positive, potential is negative. So that is how you get this term. Similarly, if you look at this m naught and this dv by dx at naught, they are in the opposite direction, so the work done is negative, potential is positive. And here if you look at this ml and dv by dx at l, so they are in the same direction, so the work done is positive, potential is negative. And so similarly, if you look at this axial force F, so F dx is the force into U is the work done, potential will be negative of that, and then for the total potential we integrate. So this is the potential of distributed force F. Similarly, this is the potential of distributed force Q. And then what is left out is these two terms, the integral term, this term and this term. So these are actually the strain energy terms. So I will explain you how you get the strain energy for this case. So now if you look at the strain energy term, strain energy, so I'm going to use the notation pi for strain energy. So now what we are saying is that now this is the beam rod, and this is the neutral axis, and somewhere this is the normal. And when it deforms, so say it takes some shape like this, and its normal is going like this. So if you look at now, initially this center point was here, so this is actually displacement u, and then if you take any point over here, so this value is going to be y times dv by dx. So if you take the displacement at any point y, so let me denote that by u. So u at any x y is going to be this u, which is a function of only x, because small u is the displacement per point on the neutral axis along x direction. So that is u minus, now this much is in the negative direction, y into dv by dx is along negative x direction. The coordinate directions are, this is x and this is y. So this quantity is along negative x direction. So the net displacement is this u minus y times dv by dx. So this is the displacement. When you look at the strain, so epsilon xx is, now because dv by dx is finite, so we will have to take the non-linear term in the strain displacement relation. So this would be du by dx minus y times d2v by dx square. So the strain epsilon xx is du by dx, d capital U by dx plus half of d capital U by dx whole square. So du by dx minus y into d2v by dx square and plus half of dv by dx square. So this is the term which is coming because of the finite dv by dx. So this term is not negligible, but this is important. So this has to be considered. So once
Sir,
you have this as a strain, yeah,
so what is capital U here, sir?
capital U is the displacement of any point at a distance x from the neutral axis.
So, sir, is it in
The
the x
small
direction
u
or
is
is it a general?
along the x direction. This is along the x direction. So if you look
Okay.
at the small u is the displacement along x direction of a point on the neutral axis. So if I take the point here, finally now this point has gone here. So the center point has moved by a displacement small u in the x direction. Then if I take a point at a distance y from the neutral axis, so that is I am taking this point over here. If you look at this point, so that point is at a distance y. So because the normal has rotated by an angle dv by dx, so that point would move in the negative y x direction by a distance y into dv by dx. So then if I take this point here, let me sketch a bigger diagram. So originally I am talking of one this point and some point here which is at a distance y. Then this has gone like this, and the normal has rotated like this, and this is the center line. So see this point along the x direction has got displaced by an amount u, and then additionally if I take any point, no this point has gone actually here. This is on the normal, so the normal has rotated by an angle dv by dx. So this is y into dv by dx along the x direction. So the net displacement, that is when you look at this distance, this distance, this one. This is u minus y into dv by dx. So that is the displacement of a point at a distance y from the neutral axis along x direction. So that is what this capital U is, and therefore the strain epsilon xx is d capital U by dx plus half of dv by dx whole square. So when you do this d capital U by dx, you get these two terms and plus half of dv by dx whole square, because dv by dx is finite, so its square is important. So we are essentially writing the Green Lagrange strain tensor, the second term, second order term in the strain displacement relation. So that's the this particular term. So is this clear?
Yes, sir.
So now
Sir,
now
how
if you
the
look at
third
the,
term in epsilon xs is coming?
pardon? Yeah, the third term is like, if you look at the strain displacement relations, so normally we take only the linear terms, but there are nonlinear terms also. So when you look at general expression for the strain, this will be du by d ax, and plus we will have the other terms like du by dx whole square plus dv by dx whole square. So these terms will be there. So in the most of the time we consider only this term, but when we consider the finite deformation, then we consider both these terms, the linear terms and the quadratic terms. Now in the quadratic term, what we are saying that du by dx is small, so this term we are not considering. We are considering only this term. So half of dv by dx whole square. That is how this term is coming. Is it clear?
Yes, sir. Thank you.
So in the strain displacement relations, when you look at the Green Lagrange strain tensor, so you have linear terms, you have quadratic terms. So for the finite deformation cases, now in this case dv by dx is finite, so you consider the quadratic term also, that is half of dv by dx whole square. So now with this, when we consider the strain energy, say pi, so pi would be half and then integration over the volume. So but that can be split into integration along length 0 to L and the integration over the cross sectional area A. And then the strain is sigma half of sigma xx into epsilon xx, and this is a uniaxial problem, so sigma xx is e into epsilon xx, so you get e into epsilon xx whole square. So this would be e into epsilon xx square dx dA. Let me first write dA and then dx. So dA dx, so this is what you will get. And now what you can do is we can write integration 0 to L integration over the sectional area is Young's modulus, and epsilon xx is du by dx minus y into d2v by dx square plus half of dv by dx whole square and then whole square dA dx. So here you get basically dx. So now, yeah, so now what you can do, you can say that strain energy pi is half integration 0 to L integration over A. Now let me do one thing. See, this term involves y, so that I will keep separate, and these two terms, let me combine them together. So I can write this whole thing as E into, now the square is like, no, square of two terms. So let me write it as du by dx plus half of dv by dx whole square. So the square of this, that is one term, plus the square of second term, so y square into d2v by dx square whole square, this term, and then minus we will have twice of y into d2v by dx square and into du by dx plus half of dv by dx whole square, and then we will have here dx no dA dx. So we will have here this dA dx. Is this clear? So then no, you can say finally that integration pi equal to integration 0 to L. Now the first term, if you look at, it is independent of the y coordinate. So the integral d, it will be simply integral dA will give you a. So the first term then will become integration ea, and then we will have this du by dx plus half of dv by dx whole square. That will be the first term. And the second term is a, now you have integral over cross sectional area, so integration y square dA. So y square dA is nothing but I. So the second term would become ei into d2 e by dx square whole square. And now this will be dx over here. So now if you look at this particular term, that is integral y dA, and the origin of y is on the neutral axis, so integral y dA will be 0. So the third term will actually be 0. So these are the two terms. So you get these two terms, and these are nothing but, no, if you look at the remaining terms what we discussed in the integral functional I. So we have one term, this half of ea du by dx plus half of dv by dx whole square dx. So this is one term, and this is the other term. So you can see both these terms. So that is this term and this term. These are the strain energy terms, and the remaining terms are the potential of the externally applied forces. So that's how you can look at the interpretation, that those two integral terms are the strain energy stored in the body. So
Sir,
this part is the bending strain energy, and this is the stretching strain energy. Yes, please.
sir, in the first term there is a whole square on the du by dx, this part.
Yeah, yeah. Sorry. Yeah, this whole square is there. Yes. Yeah. Thanks for the correction. Yes. Yeah. So, are there any questions on this? So, this is how, no, with the typical
Sir,
examples, I
hello.
have demonstrated you how
Hello.
to write the form integral functional primary and secondary variables and so on. Yeah. Yes, please.
Uh, Sir, how third term will be zero, sir? Can you please explain, sir?
Yeah.
Why
So the
D?
third term is because it is integral y dA.
Yes, sir.
So, no, cross sectional part is simply integral y dA. And if you recall the neutral axis, for the neutral axis we take, the neutral axis is these, you can say is the centroid of the cross section. So the moment of the area about neutral axis is equal to 0. So this term
Yes,
is
sir.
equal to 0 because
Okay.
you are taking the origin for y such a way that integral y dA is equal to 0. So
Yes,
for
sir.
the linear problem, that is a neutral axis. Of course, when we have this finite deformation and the axial stretching is there, although the stress is not going to be 0 at location y equal to 0, but integral y, origin of y chosen such a way that integral y dA is equal to 0, this term.
Okay.
Now we are choosing y such a way that integral y dA is equal to 0. Okay.
Yes, sir.
So now, so this is what I wanted to discuss about the weak forms. So like that, no, given problems, I think you can, now you will have some idea and you can develop the weak forms. Now let me also, so I want you to understand how one is that you can derive the finite element level governing equations from the no, directly from the integral functional also you should be able to derive. So that we would do no, many application when we consider, we will many a times take the weak form, and we will develop the take the integral functional, and we would develop the element level governing equations from there. But let me also demonstrate you how to develop the finite element level governing equations from the weak form. So now next I am going to talk about is the element level governing equations. Although this will be somewhat repetition of what you would have done in the basic FEM course, but let me just summarize that.
Sir, one question.
Yeah, yeah.
So while writing this strain energy, we have written only the x component of strain,
Yeah,
like E epsilon xx square, right?
yeah, right,
So
right.
why are we not assuming the other directions? Like
So we are,
by
see, this problem we are assuming that the rod is under uniaxial state of stress. So only non-zero component of stress is sigma xx, which is E times epsilon xx. The other stresses are zero. So sigma yy is zero, sigma zz is zero, tau xy, tau yz, and tau zx. So except sigma xx, all the stress components are zero. So we are taking the uniaxial state of stress.
okay, sir.
Yeah, which is corresponding to the basic differential equations we started with. So
But,
now when you
but
want to, yeah,
the stresses are zero in the rest direction except the x direction, but the strain will not be zero. So since we are writing the strain energy in terms that pi in terms of a strain, so we could have considered
yeah,
that
but the strain
whatever.
energy, see the strain energy is half of sigma for linear elastic body within the the linear elastic body. The strain energy is half of sigma xx epsilon xx plus sigma yy into epsilon yy plus sigma zz into epsilon zz and so on. So once the stresses are zero, sigma yy, sigma zz, and the other stresses, the only term would be half of sigma xx into epsilon xx integral dv. So that is what we are writing. Although the strains are non-zero, but since the stresses are zero, so the strain energy will only be corresponding to sigma xx term. Okay.
Thank you.
Yeah. So now coming to the how to derive the element level governing equations starting from the big form. So now what we are going to do is that let's take a finite element. So finite element means now I am taking a element, a part of the basically rod, and let us say the local coordinate system is capital X, and forces are no. I am taking the the basically of course uniaxial state of stress and only axial load. So this is let us say force is Q, and the left in we will have, let us say, the force Q1. This is node 1 of the element and this is node 2 of the element, and here the force axial force is say Q2 and the distributed force is Q, and this is X and the corresponding displacement is U. So this is the no the two noded truss element, you can say. And if you look at the weak form for this, so the differential equation is same. When we write the differential equation for this element, we will have d by dx of EA into du by dx plus q is equal to 0. So this is going to be the differential equation, and the length of the element is, let us say, small l. So capital X varies from a capital X equal to 0 at left end to capital X is equal to small l at the right end. This is the first node and this is the second node, left and right nodes. And this is the differential equation we already know for this problem. So now the weak form, if you look at, we have already done that. So the weak form is basically going to be weight function W into EA into du by dx at x equal to 0 and small l. So let me multiply the whole thing by a minus sign also. So minus here and then plus, so that the stiffness terms no is positive, as I explained you earlier. Integration 0 to L dw by dx. I'm using capital X. Capital X is the local coordinate of the element into EA into du by dx dx, and minus we will have integration 0 to L wq dx is equal to 0. So this is a weak form that you already know, we have done it. So this is a weak form, and now we want to develop the element level governing equation for this. So what we do now, the first is we need to assume an approximate solution for u within the element. So now if you look at the approximate solution, so how do we do that? So we look at in the big form or the the total the integral functional or the total potential energy functional. When we choose u, we have to see that it is differentiable up to the highest order present in the integral term. So now when we look assume the approximate solution, we consider three things. So one is the differentiability requirement. So that's basically the continuity, where you can say the differentiability requirement within the element. Then the second is the inter-element compatibility. So that is compatibility. This is inter-element compatibility here. And the third consideration we give to choose the approximate solution is that whatever approximate solution we choose, it must be a complete completeness. So it should be a complete polynomial up to the whatever highest order we are choosing. So these are the three considerations we give when we choose the approximate solution within an element. So now, here what we do, the highest order derivative of u in the integral term is du by dx. So the first order derivative. First order derivative means, suppose we assume a polynomial function, then we have to take u at least up to the linear term. So when we take the linear term, so let us say we need to have something like
Sir, only 1 minute is
yeah, hello,
sir,
yeah, I think,
time only 1 minute is left.
pardon.
Time, sir. The time.
Okay, yeah, yeah,
We have
time
tested the
value.
time.
So see, based on the differentiability requirement from the integral term, because whatever approximate solution we assume, it should be differentiable once. So now if it has to be at least differentiable once, then it should have a linear term. So say something like we are choosing a polynomial, so it should be a1 into x. Then the completeness requirement is there. So if we are having, let's say, a linear term, so before that, at least constant term should also be there. If we are having a quadratic term, then the constant linear term should be there. So that satisfies the completeness requirement. So we should have some term like a naught plus a1x. And then the second requirement is this compatibility. So compatibility means essentially across the element, primary variables should be continuous. And that means when we have the assembly of elements, so the primary variables should be continuous, and that continuity can be enforced if at the end nodes we have primary variables as the degrees of freedom. So now in this case, in this problem, the primary variable is u. So u should be there as a degree of freedom at the end nodes of the element. So if I have here value of the displacement u is u1, and the value of displacement here is let's say u2. This is node 1, this is node 2, and this is capital X. So because u is a primary variable, so it should be present as a degree of freedom at end nodes. So now since we are considering two in nodes, obviously two in nodes have to be there. So we have 2 degrees of freedom u1 and u2. So now if there are 2 degrees of freedom for the element, 2 degrees of freedom for the element, and each node has got only a single degree of freedom. So this should correspond to number of unknown terms in the approximate solution. So in this case, if we take a linear polynomial a0 plus a1x, a0 and a1 are the two unknown constants. So those two unknown constants can be expressed in terms of u1 and u2. So we can get a unique relationship. So that means for this problem, the approximate solution we can choose is a0 plus a1x. And suppose now you want to have the better accuracy element, then you can add a term a2x square. Then you have to introduce an intermediate node, let's say at the center of the element, and then you will have u1, u2, and u3, and then you can have three terms. So now this approximate solution u equal to a naught plus a1x. Let me write it as capital X, not small x. This is capital X because we are writing it in terms of element local coordinate. So now this is your approximate solution within the element. So before we substitute this in the weak form, what we do is no we express a0 and a1 in terms of u1 and u2. So for that, what we do is no u is equal to u1 at x equal to 0. So that gives you a naught is equal to uh, u1, and at x is equal to capital X is equal to L, we have u equal to u2. So that would be a0 plus a1 into L, and from this you will get a1 is equal to no this u2 minus u1 divided by L. So now if you substitute these two now in this expression a0 plus a1x, so you can write actually that u will be equal to see this u1 and plus u2 minus u1 upon L into capital X. So now you can write the u1 term together, so you can write 1 minus capital X by L into u1 plus x by L into u2, and these are no these are nothing but your shape functions. So ultimately you can write u is equal to n1 n2 into u1 into u2. So this equation I am writing, you can write it like this. So where no this is interpolation matrix H, and this is the vector of elemental degrees of freedom D. So this is H and this is D. H is the interpolation matrix and D is the element level elemental degrees of freedom. And n1 n2 are the same function. N1 is 1 minus x by L and n2 is, so you know some of these terminology, so I'm not writing that. N2 is x by L. N1 and n2 same functions are interpolation functions. H is interpolation matrix. D is the vector of elemental degrees of freedom. So now if you look at in the approximate solution, we have two unknowns u1 and u2. So we need to actually choose two weight functions. So one we will take w is equal to n1 in the Galerkin method. No weight functions are taken as the coefficient of unknown term in the approximate solution. So the unknowns are u1 and u2. So one weight function we will take as n1, another weight function we will take as n2. So now let us say let w is equal to n1, and when we take w is equal to n1, then if you look at the weak form, so we have minus no we have this n1, and then no we have this ea into du by dx. The whole thing is evaluated at 0 and L, then plus we will have integration 0 to L dn1 by dx, because it is dw by dx and w is n1, so dn1 by dx, and then we have ea, and here we have du by dx dx this term, and then we have minus of course integration 0 to L n1 into q dx. This is equal to 0. So this is what you have. Now if you look at the at no x is equal to L, this n1 will be 0. Now when you evaluate this boundary term, so at x equal to 0, x is equal to L, when you put in n1 x is equal to L, n1 is 0. So the upper boundary term is going to be 0, and the lower boundary term if you look at so we will have minus minus plus, and n1 is unity at capital X equal to 0, and this ea into du by dx is nothing but q1. So we will have actually the first term as q1, that is ea into du by dx at x equal to capital X equal to 0 is q1. So that is q1, and this term will become integration 0 to L dn1 by dx into ea, and see this du by dx again you can write it as dn1 by dx dn2 by dx into u1 u2 dx, and of course this term will be minus integration 0 to L n1 q dx is equal to 0. Are you following this? So I am trying to develop the the element level governing equation from the big form directly. So this is what we get when we take w is equal to n1. Now similarly if you take w equal to n2, the second weight function we are taking as n2. So we will have the weak form again, will be minus N2 into EA into du by dx evaluated at 0 and L plus integration 0 to L dw by dx, which is now dn2 by dx, dn2 by d capital X, and then you have EA into du by dx, and du by dx is dn1 by dx, dn2 by dx, and then here you multiply this u1 u2 dx and minus integral 0 to L and 2 q dx equal to 0. So this is what the second, no, when we take w equal to n2, this is what we will get. Hello, are you getting?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So if you have any, stop me no, at any point and ask questions. So now see again, if you look at the second term, the first boundary term over here, so n2 is 0 at x equal to 0. So at the no, lower boundary, this term is going to be 0, and at upper boundary, n2 will be equal to unity because it is x by L and x is equal to L, so L by L unity. And here into du by dx at x equal to L is q2, so we will get here minus q2 and plus of course this integral 0 to L dn2 by dAx EA, and then you have no this dn1 by dx, dn2 by dx, and you see the u1 u2 are independent of x, so you can take out of the integration sign. So here you can write dx, and then you write u1 u2 and minus integration 0 to L and 2q dx is equal to 0. So now we combine both the equations, combining both the equations, these two equations I've talked about, you get the element level governing equation. So this is how now from the big form we develop the element level governing equation. So let me take the unknown terms on the left hand side. So you can write, when you combine, you can write this as integral 0 to L. And let us say, let me write here, EA, and then first term is no
Please
dn1
extend
by
the time.
dx, second is, yeah, yeah. So see the first equation we have dn1 by dx, second equation we have dn2 by dx. So we can actually combine the two together in this manner, dn1 by dx, dn2 by dx, and then another integration of the whole thing dx. So this will be your 2 by 2 stiffness matrix into u1 u2, and this will be equal to all other terms you take onto the right hand side. So we will have minus q1 plus q2 because they are going to the right hand side, and plus we will have this integral term integration 0 to L q into this n1 n2 dx. So this is the your element level governing equation. When we combine whatever equations we get from the weighted residual state weak form by taking W as n1 and n2, we combine the equations together. So this becomes your element level governing equation. So this is how you develop the element level governing equations from the weak form. So I think, and then of course, you assuming that let's say E and small q are constant within the element, you can integrate these, get the element level governing equations, and then you assemble these and impose the boundary condition, and then solve for the unknown. So those steps, assuming that so you can do the subsequent things in the in this finite element formulation. So I want to discuss the now for the second case. Suppose we are talking about the Euler-Bernoulli beam element. So we have already developed the big form. So let us. I will just give you a brief idea, and then you can do Euler-Bernoulli beam element. So that's basically the corresponding when we are talking of the element. So we are taking this element. This as the local coordinate, and this is the y-axis. The displacement is v, and in this case the forces are basically distributed force is Q, and of course, no, let us say this is node 1, this is node 2. We have to have end nodes, and at end nodes the primary variables should be there as degrees of freedom. So another forces of course would be, let us say here the shear force is V1 and the bending moment is M1. The shear force is V2 here and the bending moment is, let us say, M2. And the for this case we have seen this is governed by fourth order differential equation. So the primary variables are V and dV by dx. So when we talk of the degrees of freedom, so we should have V at node 1 and dV by dx at node 1 as degrees of freedom. Here V2 and dV by dx at 2. So these should be there as degrees of freedom, because now we have to satisfy the inter-element compatibility, and to satisfy the inter-element compatibility we have to have primary variables as degrees of freedom at the in nodes of the elements. If we are just considering a two-noded Euler-Bernoulli beam element, we have four elemental degrees of freedom. So from the compatibility point of view, because you have four degrees of freedom, so the approximate solution should have four terms in the no the approximate solution. So that should be a0 plus a1x plus a2x square plus a3x cube. So now we have four terms a0, a1, a2, a3. They can be expressed in terms of v1 dv by dx at 1, v2 and dv by dx at 2. And so then you get what are known as the Hermite interpolation functions, and then you choose the let's say the interpolation functions are h1, h2, h3 and h4. So you choose the weight function w as h1, w as h2, w as h3, w as h4. You get the four equations, and then you can combine and you can get the element level governing equation for Euler-Bernoulli beam element. You remember for this the weak form we have already discussed. The weak form for this case is within the element, the weak form is going to be basically w into d by dx of ei into d2v by d. Let me put capital X because I'm writing for the element. So element, the local coordinate is capital X. So we have this evaluated at 0 and L. Then we have minus dw by dx ei into d2v by dx square evaluated at 0 and L. So we have already written this. Plus we have integration 0 to L d2w by dx square into ei into d2v by dx square dx, and then you have minus integration 0 to L w to dx into 0. So now from this we formed by taking w1 w as h1, w as h2, w as h3 and w as h4, you get the four equations, and then you keep all the unknowns on the left hand side and the known other quantities on the right hand side, you get the element level governing equation. So this is where I want to stop, and know if you have any questions you can ask.
So, hello.
Yeah.
So why we are taking this Hermite interpolation function in Euler-Bernoulli beam, though we didn't take in the case of that truss element and that thing. So,
Yeah, so see, if you look at for the Euler-Bernoulli beam element, the governing equation is a fourth order differential equation. So since the governing equation is a fourth order differential equation, this is the weak form. So now
yes.
we look at, if you look at the three conditions I have told you to know when we assume the approximate solution within an element, we look at the four conditions. So one is the differentiability requirement. So from the differentiability requirement, because if you look at the highest order derivative in the integral term, it is second derivative. So if we choose a polynomial, means we should choose it such a way that it is differentiable at least twice. So that means it should be a quadratic polynomial. So no, you need to have, based on the differentiability requirement within the element, minimum you need to choose is a quadratic polynomial. And the completeness, of course, is that all the terms should be present depending on whatever is the highest order term. But when we look at the compatibility requirement, that no, when we assemble the elements, one element should be compatible with the other element. So for that we need the continuity of primary variables at the across the elements, and to ensure that we need to have primary variables as degrees of freedom at the end nodes. So now primary variables are v and dv by dx. So these should be no continuous, no should be there as degrees of freedom in the element. So v1 as well as dv by dx is a degree of freedom at left node. v2 and dv by dx at node 2 has to be there as a degree of freedom, and so that is why it leads to no, now 4 degrees of freedom per element. So you should have 4 terms in the approximate solution, and these constants a0, a1, a2, a3 you express in terms of v as well as dv by dx values at node 1 and 2. So that is how you lead to the Hermite interpolation functions for the Euler-Bernoulli beam element, because of the
But
compatibility
sir,
requirement, that is continuity of primary variables across the element, that leads to the requirement of Hermite functions for the Euler-Bernoulli beam element.
but sir,
Yes,
what we saw in previous interpolation function, that we were having the freedom to take to the higher order also. Okay,
but then yeah,
so
that higher order we no higher order we will take as the due to intermediate nodes. So if you want say quadratic there, then to take a quadratic in this case, you will choose, now I have taken a linear polynomial. If you want to take quadratic, then you will introduce an additional node at the center. So the trust case, no, then if you want to take quadratic, you will have this configuration. So let us say this is 1, 2, and this is 3. So the degrees of freedom would be u1 here, u3 here, and u2 here. So you will again, I know you require only primary variables to be continuous across the elements. So at the in nodes, you need only the primary variables as degrees of freedom. So here, if you want to go for quadratic, you will take the configuration of the element like this. But for the Euler-Bernoulli beam element, the two-noded beam element itself requires a cubic polynomial, and with v as well as dv by dx as degrees of freedom at the end nodes from the compatibility requirement.
okay, so we can say that that the order of the element is nothing to do with the order of the interpolation function, right, sir?
Yeah, that see the if you look at mainly the degrees of freedom at the end nodes of the element are decided by the primary variables. So primary variables should be continuous across the element, and that is why we need them as degrees of freedom at the end node. So now the polynomial, of course, depends on three things: differentiability, inter-element compatibility, and completeness. But in this case, see, in the previous case, two-noded truss element, the polynomial is governed by the differentiability, the both differentiability as well as the inter-element compatibility lead to a minimum is a linear polynomial, and the compatibility in this case leads to a cubic polynomial, but the differentiability requirement within the element leads to a quadratic. So we take the highest, so we take a cubic polynomial. So the order of the element, no, the whether the variable and derivatives of the variable should be degrees of freedom or not, that depends on what is the differential equation order and what are the primary variables, and then the continuity of those across the element.
Thank you, sir.
Yeah. Okay. So I think the time